The term cloud offers a dangerous abstraction for systems architects. Real engineering requires operating within strict physical constraints. Amazon Elastic Compute Cloud, or EC2, provides raw infrastructure as a service. When you provision an instance, you are renting precise slice-level allocations of CPU, memory, and interfaces from physical server blades. The AWS hypervisor software sits directly on this bare metal, drawing virtual boundaries to partition the hardware into isolated virtual machines. These physical blades are housed within distinct, geographically separated availability zones. For an architect, these physical boundaries define the blast radius of a hardware failure and the inherent latency limits of the system. Designing for high availability starts with mapping these logical cloud resources back to their bare metal realities. AWS catalogs its massive compute inventory using a standardized naming convention. Take the instance type M5.2x large. The prefix M defines the instance family, which is optimized for a specific ratio of compute to memory. The integer 5 represents the physical hardware generation, integrating newer microarchitectures and improved processing performance over time. The suffix 2x large indicates the specific resource allocation size. Scaling up to the next tier within the same family proportionally doubles both the vCPU and memory. General-purpose instances maintain a balanced 4:1 RAM-to-vCPU ratio. Compute-optimized instances pivot to a tighter 2:1 ratio, leveraging high-frequency physical processors optimized perfectly for batch processing or heavy mathematical workloads. Memory-optimized instances provide a much larger 8:1 ratio to support in-memory databases and distributed caching. Storage-optimized instances are engineered specifically to deliver millions of low-latency IOPS for distributed NoSQL databases. These instance classes also dictate your baseline network throughput and EBS bandwidth limits. Sizing is an exercise in mathematical alignment, matching an application's specific bottleneck to a precise hardware ratio. Once compute is sized, it must be secured within a virtual private cloud boundary. Security groups form the primary host-level defense mechanism, regulating all inbound and outbound traffic. This firewall engine executes at the hypervisor layer, completely outside the guest operating system. These rules are strictly permissive. All traffic is blocked by default, and explicit deny rules cannot be written. The engine is stateful, meaning it automatically tracks active session states. If an inbound packet is allowed to enter, the return outbound packet is automatically permitted, regardless of your outbound rule configuration. Understanding this boundary allows an architect to diagnose transport layer failures with precision. A connection timeout error indicates the data packet was completely and silently dropped by the security group at the hypervisor level. A connection refused error means the packet successfully bypassed the security group but was rejected by the guest OS because no application was listening. Executing security at the hypervisor layer protects the instance's own memory and CPU from being exhausted by malicious packet filtering. Data persistence forces a choice between the raw speed of physical proximity and the safety of network durability. Amazon Elastic Block Store operates over a network-attached storage protocol. Because it utilizes a storage network, it inherently introduces slight latency overhead. To ensure durability, AWS automatically replicates your EBS data across multiple hardware nodes within a single availability zone. This physical replication locks an EBS volume to the specific availability zone where it was created. When workloads demand absolute zero latency performance, architects most utilize the EC2 instance store. These are NVMe SSDs slotted directly onto the motherboard, delivering massive IOPS. But because the storage is local, the data is lost if the instance stops or the host hardware fails. Storage architecture is a deliberate compromise between the safety of network replication and the raw throughput of physical attachment. A resilient system requires all these components to interact predictably under load. Scaling relies on matching software demands to these physical compute ratios. Infrastructure security relies on perimeters acting as a hardware shield before the operating system is even reached. Data integrity relies on choosing between network-attached durability and the speed of localized storage. Mastering these physical realities allows us to move past basic deployment and toward engineering systems that remain resilient, even under the stress of hardware failure.